The Pantheon has been standing in Rome for almost 1900 years. Its dome, made of concrete, is the largest unreinforced concrete dome ever built. No steel bars inside, no modern engineering tricks, no rebar, no tension cables, no post-tensioning, just concrete. And it's still there, still holding, still perfect. You can go stand under it right now and look up, and you will see the same dome that Roman citizens looked up at when it was dedicated in the year 128. Meanwhile, drive across any American highway built in the 1960s. Cracks everywhere, rebar poking through like broken bones through skin, chunks falling off bridges that are barely 50 years old. We spend billions of dollars a year patching concrete that was supposed to last a century and barely made it past a generation. So, here is the puzzle that's going to keep us busy today. The Romans built concrete structures 2,000 years ago that are still getting stronger. Our concrete starts falling apart after a few decades. Same. Basic material, calcium, rocks, water. They had no chemistry textbooks, no electron microscopes, no computers, no understanding of molecular bonds or crystal allography. We have all of those things, and our concrete is worse. Something real is very wrong with this picture, and it's worth taking the time to figure out what. Here's how to start, where I always start with the atoms, because when you don't understand something real, you have got to go down, 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 until you can see what the atoms are doing. Everything else is just storytelling until you know that I have said this 1,000 times, and will say it 1,000 more. If you want to understand anything, you have to ask, what are the atoms doing? So, what is concrete? Pay close attention to this next bit. But the paste is the interesting part. The paste is where the action is. In modern concrete, that paste is made from something real called Portland cement. Here's how you make it. You take limestone, which is mostly calcium carbonate. If you remember your chemistry, that's one calcium atom bonded to one carbon atom bonded to 3 oxygen atoms, all stacked together in a crystal that you would recognize as chalk or seashells or the white cliffs of Dover. You grind those nodules into a fine powder. That powder is Portland cement. Now you add water and something real, wonderful happens. The calcium silicates reach out and grab onto the water molecules. Not gently, they react, rearrange, form entirely new crystal structures, little needles and plates and sheets that interlock and bind everything together like microscopic fingers gripping each other. Imagine pouring water onto a tray of dry spaghetti, and the spaghetti instantly weaves itself into a fabric. This is the part that changes everything. That's the chemical reaction happening right under your hand. Atoms finding their partners and settling into their new arrangement, releasing a little burst of energy with each new bond. In a big pour, like a dam foundation, the heat can be a real problem. It can actually crack the concrete from within if you aren't careful about managing it. And here's the key thing about Portland cement concrete. Once those crystal structures form, that's essentially it. The crystal lattice is built. It has found its final configuration, and it's not going to change. And here's the problem with any rigid crystal lattice. If you crack it, it stays cracked. Think of it like a window. Glass is a beautiful, strong, transparent material, harder than you might expect. Think about this carefully. When a crack forms in modern concrete, it's an open wound that never closes. Water gets in. It carries dissolved salts and acids. It reaches the steel reinforcing bars buried inside, and those bars begin to rust. Rust takes up more volume than the original steel. Eventually, the rebar rusts, the surface spalls, and the highway department comes out with jackhammers and orange cones and a budget overrun. This is why highways fall apart. It's not that the concrete was bad when it was poured. It's that concrete has no immune system. It cannot respond to damage. It's a dead material, chemically speaking. When a volcano erupts, the explosion shatters minerals into tiny fragments with enormous surface area. And those fragments are chemically hungry. They're full of silica and aluminina in a disordered reactive state. When you mix this volcanic ash with lime and water, the silica and aluminina attack the calcium hydroxide and form extremely strong, extremely stable compounds: calcium silica hydrate and calcium aluminate hydrate. Tight, interlocking crystals that resist water, resist stress, resist time. Mystery solved. But that cannot be the whole story. And you should be suspicious whenever someone tells you a mystery is solved by a single ingredient. Nature is rarely that simple. Here is why the volcanic ash explanation falls short. Not all Roman concrete survived. Something real else is going on. And here is the clue that kept nagging at researchers. Firm in the really durable Roman concrete, the stuff that survived earthquakes and centuries of rain and even constant battering by ocean waves, they kept finding these little white chunks, millim-scale lumps of calcium scattered through the matrix like raisins in a cake. You could see them with the naked eye if you broke open a sample. Little white spots in a gray background. There is an ancient tomb on the Via Appia, the famous Roman road leading south out of Rome. The tomb was healing itself right there on the road out of Rome. The evidence was staring everyone in the face. For decades, the scientific community looked at those white lumps and collectively shrugged. Poor quality control. They said. The Romans did not stir their concrete well enough. Some lime failed to dissolve. Scanning electron microscopes, energy dispersive, X-ray spectroscopy, powder X-ray diffraction, confocal Raman imaging. They mapped the chemical composition of those lumps atom by atom, and what they found changed the story completely. Those lumps are something real called lime classes, and they aren't a mistake. They're the whole secret. To understand what a lime class is, you have to understand two forms of lime, and the difference between them matters enormously. Now, here's where it gets stranger. It gets so hot it can boil the water right off. The reaction releases about 65 kilojoules per mole. For comparison, that's enough energy that a large pile of quick lime with water poured on it can actually catch nearby materials on fire. The medieval English Navy reportedly used quicklime as a weapon, throwing it at enemy ships to blind the crews. Now, the assumption for years was that the Romans were careful. They would take the quicklime and slowly add water to turn it into calcium hydroxide, which is called slate lime. This technique is called hot mixing. You take dry quicklime, volcanic ash, water, and aggregate, and you combine them together. The quick lime reacts with the water violently. The temperature spikes. The whole mixture gets blazing hot, possibly locally reaching temperatures of several hundred degrees. That extreme heat accelerates and alters the chemical reactions happening in the mix. Here's what most people don't realize. The dry, quicklime and volcanic ash were staged for combination, not pre-slaked. This wasn't some regional quirk or one builder's experiment. This was standard practice, at least at this site, preserved by the very volcano that supplied their raw materials. The irony is almost too perfect. But back to the chemistry. During hot mixing, not all of the quicklime fully reacts. Imagine the concrete is like your body, and the lime cloths are like little capsules of medicine stored under your skin. As long as everything is fine, they sit there quietly. They don't react, they don't interfere. But the moment a crack forms, everything changes. Most people stop asking questions here. Then, as it encounters carbon dioxide from the air, or as it simply dries out, the dissolved calcium precipitates as calcium carbonate. New mineral crystals growing right there in the crack, filling it, sealing it, gluing the two sides back together. The crack heals itself. The concrete repairs its own wound. Massic's team tested this in the lab. They manufactured concrete using the Roman hot mixing method, let it cure and harden, then deliberately cracked each sample. The Roman method, using nothing but lime and volcanic ash and heat, outperformed them all, and it costs almost nothing extra. You just have to be willing to let the mixing get hot and messy. And this mechanism doesn't just work once. Every time a new crack forms and water enters, it can trigger the same response as long as there are lime clusts nearby. And those clusts are distributed throughout the entire matrix, scattered everywhere like a distributed immune system. Every crack triggers its own remedy, and all of it happens without any intervention, without any engineer, without anyone even noticing, just atoms following the rules of attraction and repulsion. I once said, if all of scientific knowledge were to be destroyed and only one sentence could be passed on to the next generation, the best sentence would be this: all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling upon being squeezed into one another. In that one sentence, there is an enormous amount of information about the world if just a little imagination and thinking are applied. Roman concrete is a perfect illustration of that principle. Given the right arrangement of materials, self-healing isn't just possible, it's inevitable. Now, here's how to push deeper, because there is yet another layer to this mystery, and it involves the ocean. Some of the most impressive Roman concrete is found in marine structures, harbor walls, and breakers that have been sitting in salt water for 2,000 years. Seawater is devastating to modern Portland cement concrete. The salts corrode the rebar. It normally requires very high temperatures and specific pressures. But in Roman marine concrete, it grows naturally, slowly, grain by grain, as seawater seeps through the material over hundreds of years. Butari reinforces the concrete from within. It fills pores and strengthens the binding matrix. So, Roman marine concrete isn't just healing its cracks with calcium carbonate. It's growing entirely new, reinforcing crystals inside itself using the very seawater that would annihilate modern concrete. They did not fight nature. They built something real that works with it. Whether they understood the mechanism or not, the result is the same. Their approach was in a very deep sense more physically intelligent than ours. That's not just clever engineering. That's engineering in harmony with the physics of the situation, that calcium hydroxide reacts with volcanic ash to make the strong matrix. Then, when a crack forms and water gets in, the lime clasps dissolve and the calcium meets carbon dioxide from the air. And what does it form? Calcium carbonate, limestone, the very thing you started with. It's a circle. The evidence for this is solid. And calcium carbonate breaks down in fire, does its work as concrete, and quietly reassembles itself from water and air. There is a kind of elegance there that you couldn't design better if you tried. Now, the practical question. Modern concrete production accounts for roughly 8% of global carbon dioxide emissions. 8%. That's enormous. You don't need to invent some exotic new technology. You just need to make what we already have last longer. And the Romans showed that this is physically possible, not theoretically possible. Actually demonstrated, proven over 2 millennia of real-world testing. Several groups are now working on exactly this, inspired by the Roman discovery. Some are experimenting with hot mixing techniques using quicklime. Others are using coal fly ash, which has chemical properties remarkably similar to volcanic palena, as a substitute. The physics here is remarkably clear. We optimized it, standardized it, made it cheap and fast and uniform. We rejected any batch that had white lumps in it. We called those imperfections. And the result is a material that falls apart within a human lifetime. The Romans used a method that was violent and messy that produced chunks and irregularities we would throw away on a modern construction site, and their buildings have outlasted every civilization that came after them. Sometimes the imperfection is the feature, and every raindrop that reaches a lime class triggers a microscopic chemical reaction. Calcium dissolves. It flows into the crack. It meets carbon dioxide. It crystallizes. The crack seals. You don't need to build a bridge to enjoy understanding why a bridge stands up, but every once in a while understanding actually helps you build a better bridge or a better dome. And sometimes the best way to build for the future is to look very carefully, very humbly at what the atoms were doing in the past. If there is one thing you take from today, let it be this. What part of this surprised you most? Drop it in the comments below.